Why are we going to have to abort this proof? Okay, we're about 2/3 of the way through. Everybody turn to your neighbor, and for the next 2 minutes, try to figure out why this proof doesn't work. And whoever's brave and courageous and gives the most concise, crisp, clear explanation, after 2 minutes, I'll buy you a drink of your choice. Go.
Maybe it's good to print the definition of reachable prime. Yeah, let's see.
Yeah, I think we have to go to the. It's still too big.
Is that a word for it? Is it reachable prime that you want to print?
You got me. Good call.
It is, but what is
Okay, who's got it? No senior faculty. We're only. Who among you is courageous?
This is just a guess, but maybe the induction will fail. Do we need like some kind of step indexing here, for example?
Nothing so fancy.
Okay.
But yeah, that's exactly right. The induction's not going to work. That's absolutely right. Yeah?
We know nothing about the state.
Yeah. You both get beverages of your choice. Right, so what's going on, right? So when we do induction, what are we trying to do? Right, we're saying that, we're going to end up, we need to prove this by induction. It's the only thing we really have to reason about reachable prime, right? And it's just not the case that knowing all the outputs are fresh is enough to know that if I take one more step, the thing I'm going to output won't have been something I already saw, right? If all you know about a state is that up until now all its outputs are fresh, that's all you know about it. You don't know anything about it's all you know about a world, right? All you know about the world is that up until now all of its outputs were fresh. That's just not enough to prove that the next thing it outputs won't have been something it already sent. So we can, it's usually useful, it's often useful to go ahead and, even when you know it's not inductive sometimes, if you don't see what's going on, to grind through the proof. So in this case, right, we do the normal thing, induction, base case is easy, outputs are fresh in the initial world, no problem. Here we're going to say, okay, well, suppose that I got to some state W1, and then I took one more step in the ideal semantics, one more step to get to W2. I want to know the outputs are still fresh. Now, what resources do I have at my disposal to prove that? Right? Remember, we're always playing this game of exchange. So Cox said, look, you've got these four things, you give me one of those. So we need to use those to try to prove this. So we have this inversion tactic. And what it's going to do is going to say, well, okay, Cox, tell me how you got that step, that H you're telling me about. What kind of step was that? And Cox's going to come back and say, well, how about an input step, right? So we're going to handle the input case. Now here, what we want to do is we want to get at what's going on in the handler, right? So Cox is telling us, yeah, I ran your handler, and it produced this stuff. And I want to be able to relate those to each other, right? So I want to simple that. I want to sort of run that handler. And sure enough, I can do that. Let me change it back to vertical. I think that'll line wrap better. Maybe. Nope. I'll play around with fonts before tomorrow. We'll find something that works. Okay. Right, and so now what I want to do is I want to prove outputs are fresh on this state, this new world that I got after I ran my handler. And here's where I get stuck, right? Here's what I'm left with. So this is what we mean when we say, just knowing that all the outputs you've produced had no duplicates, they're all fresh. Just knowing that just isn't going to be enough to say when I take one more step, it continues to be true. And we see it here, right? What I know is that up until W1, all the outputs were fresh. And now what I need to do is I need to prove that there's no duplicates in the current state of the server, right? That's the thing it just output, followed by the outputs up to W1. But I have nothing in my context that lets me relate anything about the server's current state to anything that happened before, right?
I think that's not quite true.
Well, I still have reachable.
This is still true.
Yeah. It's going to be a lot easier. This is not like, yeah, so I still have the reachable fact, right? So I could sort of start over here. I don't have to actually back out, but any good engineer would. Okay, yeah. So, yeah. All right. So now we're going to abort, right? We're going to prove something different. What do we need to do, right? So we figured out that we need to relate the state to the trace. Here are a few little helper things, but the main thing we want to prove is we're going to prove this fact, right? So we're going to prove that for everything in the outputs, right? If the server ever output a value, if it ever handed that natural number back to a client, then it's the case that the current state of the server is bigger than that number, right? And it turns out this is inductive, right? Because we bump our state whenever we hand back a message. So we're going to be able to sort of chain this together and get the proof we want. And that just goes through, again, as you might expect. The base case is pretty easy. It's about as easy as you can get it. And the inductive case also goes through pretty simply. And now we can prove a little helper lemma that just says that it's never the case that the node's state is in the outputs, right? And once we have this, we can return to our proof. And when we get to that nasty inductive case, right? So this is where we got stuck earlier. Now what we can do is we can bring that lemma to bear. We're going to invoke a lemma about no dupe from the standard library. And now this is exactly what our lemma had in it, right? So this is what, this is a small version, but this is the game that you have to play when you prove distributed systems correct. So the main one, then we'll talk about it more on Friday, that we've done in Verity is called Raft, which is a distributed consensus protocol. And it's actually one of, it was a guy named Diego's PhD thesis. And in his thesis, he wrote down what he thought were all the invariants necessary to prove the system correct. And it turns out that I think we needed a lot more than that. And also the ones that he wrote down, several of them weren't inductive. Right? So they weren't even powerful enough to keep establishing themselves as the system ran. This is the guy who made the system. Super smart, right? Huge impact, like incredible researcher, great hacker. It turns out that it's just really hard to figure out which invariants are inductive. Right? And that's a skill that you sort of hone and develop over time. And there's a lot of trial and error in it. But that's how it works. Okay, so with the time we have left, I wanted to show another network semantics. I thought maybe we'd have folks do it, but I think in the interest of time, maybe let's go ahead and crib from our secret stash down here. Oops. So earlier someone mentioned like, hey, isn't this ideal semantics pretty bogus? Like delivering messages in order in a network? Don't you know that switches have limited buffers, and when they fill up, packets start dropping? Don't you know that people duplicate packets, they take different routes? So they change order, or sometimes they get duplicated. Like, all kinds of bad stuff can happen in the network. So I wanted to show you a step towards a slightly more realistic network semantics. And there's suggestions for some other ones that you might try to define. And it's designing these is a little bit tricky, but can be pretty interesting. So here, interesting. Here we're defining another semantics that has a little bit more failure than the previous one, right? So we still have an input step that looks a heck of a lot like the ideal semantics, right? You get an input, what are you going to do? You're on the handler, and you're going to put the stuff on the network and send back outputs. There's not a whole lot of option there, right? But for the network, things are a little bit different. So in particular, remember before when we said we did an ideal step, we gave two explicit worlds, and we just talked about the network and the world that we started from. Here we have something a little bit different. Here we just have a hypothesis, and all it tells us is that the packet we're going to deliver is in this world we're starting in, right? So it's some packet in the network, but we have no idea which one, right? So now things can be arbitrarily reordered. They can also be arbitrarily delayed. Right? There's no guarantee that eventually a packet gets delivered. So this is a lot more this is a slightly more realistic model of a network. As we'll see later, there's a bunch of stuff that can happen. Okay, and because of the way we define things, all of our other definitions still just work. Let's look at an actual system with two nodes that we're going to reason about in terms of this semantics. Oh yeah. Okay, so here we have a slightly less trivial system that is somewhat related to the fresh system. So now we're going to have a distributed system where all the nodes track NATs, and clients can request for those NATs to be bumped. Now this system does do something slightly interesting, which is that there's a relationship between the two nodes in the system, the primary and the backup. In particular, only the primary interacts with clients, right? The backup ignores clients. It doesn't do anything in response to their inputs. It never sends them outputs from messages. And the backup's only going to bump its state. It's only going to increment its counter when asked to by the primary, right? And the primary is only going to respond to a client when it hears that the backup has bumped its counter. Right? So now what we know, right, the intuition, is that clients only get a response if the result of their request, that bumping, has been replicated on two nodes, right? So we have some more faith that like an act of God isn't going to completely obliterate our data. So let's see how we define the system. It's the same game we were playing before. We have the base params. We define input and output. So clients they can request a bump. They can hear back they got a bump. There's two nodes, primary and backup. Nodes are their states NAT, and they exchange INC and ACK messages. Now here we're going to define another command just because it's handy. Right? We're going to define this do INC command. And all it does is a get followed by the bump. We could have used this in fresh. And now we're going to write the handlers, right? So now we have two different kinds of nodes. So one of the things you'll notice, this is also true in Verity actually, right, is that all nodes have the same type, which is not very realistic. This should actually be a dependent type should be indexed by the node name or something. You can totally imagine doing that. It's not that tricky. So here, when we handle input at a given node, we're first going to match to see what kind of node we are, right? So if we're the primary, and our client says, hey, can you bump your counter for me? We'll bump our counter, but instead of telling the client that we bumped the counter, giving back that number, we're actually going to send a message to our friend backup, and ask backup to bump their counter, right? Now, if we're not the primary, if we're the backup, we do nothing, right? And again, we're just doing this all in the same monad. Handle message is sort of the other end of this. So we're trying to handle a message, and we're the backup. If we get a message that's an inc, we do it, and we tell the primary that we did it. Otherwise, we don't do anything, right? So if somehow, well, it's not possible in any reachable world for backup actually to get any other message, but if it was, it wouldn't do anything. And primary, similarly, if it gets a message that's an ACK, it'll actually output to the client that the ACK is now replicated, right? It's going to say, hey, bump is done on me and backup. Okay, does this make sense? People okay with this?
Ideally, we'd like it so that the backup node isn't visible from the outside, so you can send an input to backup. How would you model that?
So, I mean, you could make the input and output types dependent on the node they were attached to. I mean, there's a bunch of ways you could define this. I think that there are sort of, yeah, that's a good example of things that are unsatisfying with this the way we're defining it. This is definitely implementable, though, which is a nice thing, and it's very simple. But I think that getting the way you define clients right is actually very important. And this is not sort of the last word on that at all.
So it seems impossible to observe in the trace that your system is working correctly.
Yeah, so what you want to know is that when I respond to a client, I want to know something about the backup state, but the backup state isn't in the trace. So you can't write that down. Yeah. It's not a spec about the external interactions with clients. It's fundamentally an internal spec. So, we can still prove it, but I can't write it. If I just hand you a trace, you can't give me that. You can't tell me if that property holds or not. So it's actually a very nice point. Thank you for what is it called in sports? Alley-oop? Yeah, that's it. Okay, right, so one thing that you should think about is how you would write a trace space spec for this counter system. Right? What could you know about this system that would be interesting to know just from the trace? But as Andrew pointed out, right, what we really want to know, well, this is not what we really want to know, right? Actually, a great spec would be to prove that you want to, for every world, actually this is going to be a little bit trickier. As soon as I send a message to a client, I know something about the state at that point. So I have to do something with the reaches. Yeah.
What you really want is modeling failure and having clients start sending inputs to the backup, and then say that whole thing presents the illusion
is transparent.
Service.
Yeah. So there's a bunch of different specs, right? So one thing I might want, as it's a thing I kind of said in English, is that whenever I say something back to the client, it's been replicated. And that's a little bit tricky to do, right? We're going to have to.
It's not what you actually want. The client doesn't want to know what replicate means.
Well, for this system, that's what this system is designed to do. This backup is behind a firewall for other reasons or something. We don't want this backup to interact with clients, whatever. The second point, though, is that actually that's not even, as I'm saying, the ideal spec, right? So most of the time when you do primary backup, you do it so you have sort of graceful failure, right? If the primary fails, the backup steps in and service continues. Again, the whole point of distributed systems is that even when there are faults, you can continue to offer service. And so that's sort of the spec you would ideally have, which this system isn't even designed to do. Okay. So instead, we're going to start with this much simpler trace-based spec. Oops. And all we're going to do we're just going to prove that the backup's never ahead of the primary, right? But it's going to turn out that's enough that we're going to be able to see a few things in